Okay, so here is the general procedure for solving a truss. The first thing you're going to do is you're going to free body diagram your truss, and you're going to replace the pin and roller supports with reaction forces. Okay, so we are working on truss number 4, and I'm going to go ahead and free body diagram that truss. So the free body diagram that we start out with is not what we're going to end up with, because we're going to make changes to this as we go along. And we had a pin support here at the top, so I'm going to put in the pin support, and I'm just drawing the arrows in just any old way, and then we'll figure out as we go along how the arrows are supposed to be. And I'm going to label these joints. Here we have joint A, here we have joint B, and here we have joint C. And at C, we have a 50-pound weight. And then I'm going to change this 50-pound weight for your 6 weeks test on this. This is going to be the truss for your 6 weeks test, and I'll change that weight. We also know that this is 3 feet, and this is 3 feet. Okay. So once we have our truss free body diagrammed, then we try to figure out the direction of the reaction forces. So you imagine if you were holding this object and what direction the forces would have to be applied in order to keep this still. So here at the pin joint, it has to hold it up. So this reaction force needs to change direction. So I'm going to put this reaction force as up. And at the pin, it's attached to the wall. So in order to be attached to the wall, this reaction force needs to be the other direction. Okay, and if this reaction force were in this direction, then the whole bottom part of this truss would kind of swing to the left. So we don't want it to swing to the left. It needs to be stabilized. So at the wall here, the reaction force is going to push in the other direction. And you just kind of have to reason your way through these reaction forces. And as we saw with that bigger truss, at the pin, your reaction force is going to pull one direction, but it's going to be a support force from underneath, and it will be a support at the roller as well. This reaction force at A is going to be a roller, or we replaced a roller. Okay, let's label these reaction forces. So we have reaction force at B in the X direction, reaction force at B in the Y direction, reaction force at A in the X direction, and then over here, this 50 pounds is going to be the force at C. Okay, so we just completed step 1, and you should have these steps written down from when we went through these steps the other day. So does anybody remember what the second step is? Yes, we find the angles. So we have a 90-degree angle here. We're 3 feet off here. We're 3 feet here. So that means we could go ahead and plug in, and we could say the tangent of the angle is equal to the opposite over the adjacent side. And then we could go ahead and plug in values there. So the tangent, let's see, the angle is going to be equal to the inverse tangent, and then plug in the values 3 feet over 3 feet. And then we solve for the angle, and we see that the angle is going to be equal to 45 degrees. And of course, the angle we were talking about was here at C. So this is a 45-degree angle. And it would be the same over here. But you could just reason yourself into seeing these as two 45-degree angles. All right. The next thing we do is solve for the reaction forces. So I'm going to label reaction forces. And in order to solve for the reaction forces, what do we do?
Put the sums of the forces instead of the division.
Yes. We have the sum of the forces in the x direction. We make that equal to 0. The sum of the forces in the y direction. We make that equal to 0. And then the sum of the moments on this truss. We make that equal to 0. So here are our equations that help us solve everything on a truss. So in the x direction, we have the reaction force at A in the x direction, which is in a positive direction. So we're going to call it the reaction force at A in the x direction. The reaction force at B is in the x direction, but it's a negative force, so I'm going to subtract it, and I'm going to call it the reaction force at B in the x direction. I'm going to make those equal to 0, and when I do, I see that the reaction force at A in the x direction is going to be equal to the reaction force at B in the x direction. So if I can find one of them, I found the other. And I'm going to leave it there, because that's as far as I can get with our known values until I know more. Okay, now let's look at the y direction. What do we have in the y direction? Yes, we have the reaction force at B in the y direction. Is that a positive or a negative value? Positive, because it's going up. What else do we have in the y direction? 50. Is that a positive or a negative value? Negative. It's going down. Okay, so I'm going to subtract 50 pounds, and I'm going to set that equal to 0. So now look what I found. The reaction force at B in the y direction is equal to 50 pounds. I just found one of my reaction forces. I'm going to go up here and label it. Bless you. Okay, so I'm now going to use the sum of the moments. So a moment is a turning motion. So the only point about which this truss could turn is here at the pin at B. Okay? So this pin joint will allow for rotation. So all of my moments are going to be about B. These two forces cancel each other out. We don't take them into account when we're calculating moments, because they start at 0. So the distance is 0. So the only forces we're going to take into account is everything that's some distance from B. Okay, so the sum of the moments, let's see, what are my moments? I have a moment at A, okay, so this reaction force could cause rotation in this direction. What do we call this direction? Counterclockwise. So is that going to be a positive or a negative moment? Positive. Okay, so we have the moment at A, and it's positive. What's our other moment?
Let's see.
At C. Okay, so at C, we could have rotation in this direction. Is that going to be positive or negative rotation? It's clockwise, right? That's the way the handle on the clock turns. So it's negative. So we have a moment at C, and we're going to set those equal to 0. So once we find the moment at A, it's going to be equal to the moment at C. And let's now, at this point, break the moments down into what comprises a moment, which is what? Force and distance. So the force at A is going to be the reaction force at A in the x direction times the distance at A, and that's going to be equal to the force at C, which is a known value, 50 pounds, times the distance to C. And remember, that distance has to be a distance that's perpendicular to the force. So here's our force, and here's our perpendicular distance. So we have to recall the L-shaped wrench scenario here. This is the distance we're talking about, 3 feet. Okay, now we're going to solve for our unknown value. And what is our unknown value in this equation? Right, the reaction force at A in the x direction. So when we're solving for that, we're going to just divide out the distance at A. And so our reaction force at A in the x direction is given by the force at C times the distance to C over the distance at A. Okay, plug in values. Force at C is 50 pounds. Distance at C is 3 feet. Distance to A is 3 feet. Cancel 3 feet, cancel 3 feet, and we see that reaction force at A in the x direction is equal to 50 pounds.
And since that's equal to the reaction in B, it's the same.
Yes, and that means that we've just found the value of the reaction force at B. So 50 pounds is equal to the reaction force at B in the x direction. Okay, on your 6 weeks test tomorrow, am I going to have to show all this work? Yes, you have to show all this work. Okay, so now I'm updating my truss diagram. I found my reaction forces. So now we're going to go to this truss diagram and we're going to make some changes here. We're going to isolate the joints. So I'm taking out the beams, and we're going to assume these beams are in tension, which we show like this. Until we have a sign change in our calculations, we're going to assume everything's in tension. Okay, and let's label these beams. So we have AB, BC, and AC. So the last thing we're going to do here is find the values of the forces that are acting on each one of these beams. And we only have 3 joints, so this one's easy. And when you're picking the joint to work with first, you want to try to pick the easiest one. So I know that A is the easiest one because we have a known reaction force value, and we have no components that are taken out of the X or Y direction. Everything is completely in X and Y. So A is an easy one to start with. So let's start with A. So we're using the method of joints, and you just pick a joint. And you're not going to solve if you have a really difficult truss, you're not going to solve everything right off the bat. Like you may have to go from one joint back to another joint as you get little reaction component forces figured out. All right, so here's joint A, and we're going to draw joint A, assuming everything is in tension. So here's AC. Here's AB. Here's our reaction force at A in the X direction, which is a known. We found that to be a 50-pound force. Okay, so I've got my joint drawn. Now what do? What would be my next step? Yes, if I had anything out of X and Y, I would draw in component arrows. So if AB happened to be off in this direction, then I'd draw an AB in the X and an AB in the Y direction. Okay, but I don't have to do that, so now what do? Yes. Okay, so the way I solve for the forces is I use my sum of the forces equation. Sum of the forces in the X direction are equal to 0, and the sum of the forces in the Y direction are equal to 0. Okay, so in the X direction, we have the reaction force at A in the X direction, and we have AC. We're going to make that equal to 0. The reaction force at A in the X direction is 50 pounds. AC, we don't know the value, equal to 0. And we see that if we solve for AC here, we're going to find AC to be what? Negative 50. We had a sign change. It went from positive to negative. So that tells us that AC is a 50-pound force, but it's actually in compression. So now we got to go back here and we've got to redo our diagram, and we've got to change AC to be in compression, so it's going to point towards the joint. And then let's also go back up to our main diagram here, and let's change the direction of AC. And let's call AC a 50-pound force in compression. In the Y direction, sum of the forces in the Y direction are equal to 0. I already wrote that down. Okay, in the Y direction, we have no forces in the Y direction on this joint. We have a member, AB, but there are no forces acting in the Y direction. Everything is completely in the X. So we're going to therefore say that the force on AB is equal to 0. And so if you were working on that and building that, you could make AB a very light member. It doesn't have to be structurally strong or expensive. Okay, so let's call AB 0 pounds. And it's neither in compression or tension because it's not experiencing any forces. Okay, so all we need to find now is BC. And we can just go to C now, to joint C, to find BC. And once we've found BC, we're done. We don't have to do anything else. So we're going to draw joint C. At C, we have a 50-pound force. We found C to be in compression, so it's going to point toward the joint at C. And we found AC to be 50 pounds. And then BC is our unknown. We assume it's in tension, so we point it away. See, this is AC. Okay, what do I do now? Break it down into the X and Y components. So what am I breaking down? It's going to be BC because it's at an angle. So BC has a Y component, which we're going to call BC in the Y direction, and BC has an X component. Which way do I point the BC X component? Yeah, to the left, because BC, the sense of the BC line is up and to the left. So when I draw in my component, I'm going to point it in this direction, which means it's going to have a negative value. Okay, this is BC in the X direction. Okay, so now I do my sum of the forces equation. Sum of the forces in the X direction are equal to 0. Sum of the forces in the Y direction are equal to 0. Let's work on that X direction. What do I have in the X direction? I have BC in the X direction. What else? Yes, AC, which is 50 pounds. Okay, so I have a positive value for AC. Do you see that? Why AC is positive? AC is pointing to the right. So we're going to give it a positive value. BCX is pointing to the left. So we're going to give it a negative value. Negative BC in the X direction. And that's going to be equal to 0. Plug in my value for AC, so that's 50 pounds, minus BC in the X direction, and BC in the X direction is going to be equal to 50 pounds. Okay, but I don't care about what BC in the X direction is. I need to find BC, but now that I know the adjacent side, the value of the adjacent side of BC, I can use my cosine function and my known value for the angle to find out the value of BC. So that's what I'm going to do. The cosine function, the cosine of the angle, is equal to the adjacent side over the hypotenuse. Okay, look at this diagram and make sure you can figure that out. This is what I want. This is the hypotenuse. This is the adjacent side. So the only unknown value I have in my cosine equation is the hypotenuse. Okay, so now I plug in values. The cosine of 45 is equal to 50 pounds, that's BC in the X direction, over BC. I now solve for BC, and I should find that BC is equal to 70.7 pounds. There was no sign change, so we keep it in tension and update the diagram. Okay. Now, for my sum of the forces in the Y direction, I already found everything I need to know, so I don't have to keep going. This truss is solved. And please do put little boxes around your your beam values when you find them so that I can find them easily on your paper. Any questions? Okay.